Stoichiometry, what is it and how do we do it? The word stoichiometry comes from the Greek word stoichion, which means element or elemental, and metry, which means to measure. So it basically means to measure elements. You can think of it as measuring stuff. And what stuff are we going to measure? We're going to measure particles, moles, mass, and volume. And probably a more clear definition of stoichiometry is going to be the calculation of quantities from balanced chemical reaction. Evident or give emphasis on the word balanced because you need to know the ratios of substances in balanced chemical reactions. So given the stoichiometry diagram, we've already learned to convert moles to particles using Avogadro's number, multiplying when we go outward, dividing when we go inward. Same for moles to mass, using the equivalent 1 mole equals the molar mass of a substance. You multiply by the molar mass when you calculate grams. You divide by the molar mass when you calculate moles. Same for volume. 1 mole equals 22.4 liters. So to go from moles to liters, you multiply by the 22.4. To go from liters to moles, you divide by the 22.4. The only real new step in stoichiometry is going to be this middle step here, calculating moles to moles. You'll be given one substance and its quantity in a chemical reaction, and you'll be asked to calculate the unknown in a certain quantity, either liters, grams, numbers of particles. And to get from the known to the unknown, we have to go from moles to moles, and the number there comes from the balanced chemical reaction. So again, moles to particles, Avogadro's number. Moles to mass, we use the molar mass. Moles to liters, we use 22.4. The new step again, moles to moles, we use the number from the balanced chemical reaction. Here is a very simple stoichiometric problem. We want to balance and determine the relative quantities of particles, moles, mass, and volume for this equation. Again, always first thing you got to do is balance the chemical reaction. Here we've only got one nitrogen on the product side. There's two nitrogens on the reactant side. So we have to double the nitrogen dioxide on the product side, which then makes us double the oxygen on the reactant side to get a balanced reaction. And so again, the four quantities of stoichiometry are particles, moles, mass, and volume. From this reaction, we can see there's one nitrogen for every two oxygens and two nitrogen dioxides. So that gives us a ratio of particles. It's a 1 to 2 ratio. Moles are the same ratio. We can think of these particles as moles. And so there's 1 mole of nitrogen for every 2 moles of oxygen, for every 2 moles of nitrogen dioxide. For mass, again, now we have to go to the periodic table. We've got 1 mole of nitrogen, so that's 28.02 grams. 2 moles of oxygen, that's going to add up to 64.00 grams. And then 2 moles of nitrogen dioxide, we can either calculate that from adding all of the product together, or we can add the masses of the reactants together. 28.02 plus 64 gives 92.02. So those are the equivalents or the ratios of the masses of each of these substances in this balanced chemical reaction. And for volume, 1 mole is 22.4. So if we have 1 mole of nitrogen, that's going to be 22.4. 2 moles of oxygen is going to be 44. And 2 moles of nitrogen dioxide is also going to be 44.8 liters. And so there is a law of conservation of mass. The mass of the reactants must equal the mass of the products, but there is not a law of mass or law of conservation of volume. The volume of the products does not have to equal the volume of the reactants. Here is a stoichiometric problem that is going to be a mole to mole conversion. So we're told that nitrogen gas reacts with hydrogen gas to form ammonia gas, and from that we can write the balanced chemical reaction. And so we write the balanced chemical reaction, and now we're asked to determine how many moles of ammonia. So this is our unknown, how many moles of ammonia if you start with 3.40 moles of hydrogen gas, so that is our known, and so this is just a mole to mole problem. And again, in the balanced or in the stoichiometry diagram, we are just going from moles of known to moles of unknown, so one step. And again, the mathematical relationship for that comes from the balanced chemical reaction. So we always write down the known. We're given 3.40 moles of hydrogen gas. Note from the balanced reaction, there's 2 moles of ammonia for every 3 moles of hydrogen. So we're going from moles of hydrogen to moles of ammonia. So we want to put moles of ammonia on top and moles of hydrogen on bottom. That way the moles of hydrogen cancel with the moles of hydrogen, and that calculates out to be 2.27 moles of ammonia. But again, this middle reaction is the only new step in stoichiometry that we have not covered to this point, and now we just use the balanced chemical reaction ratio numbers to calculate that step. And so if we're going from hydrogen to ammonia, we want 2 over 3 because there's 2 moles of ammonia for every 3 moles of hydrogen. Let's try one that's a little bit more complicated. This is going to be a mass to mass conversion. For the same reaction, what mass of ammonia will be produced if 44 grams of hydrogen are used, assuming a sufficient supply of nitrogen. So now, instead of wanting to find moles of ammonia, we want to find grams of ammonia given 44.00 grams. So now if we look at our stoichiometry map, we are given grams of the known, grams of hydrogen, and we want to find grams of the unknown. So we want to find grams of ammonia. And so we're going to have to go from grams to moles by dividing by the molar mass. Then we're going to have to go moles to moles using the numbers from the balanced chemical reaction. Then we're going to have to go moles to mass by multiplying by the molar mass. I prefer really to use the balanced chemical reaction as a map. We have to go from grams to moles, moles to moles, and then moles to grams. And so this is a grams to moles to moles to grams, grams of known to moles of known, to moles of unknown, to grams of unknown. So we're starting with 44 grams of hydrogen. To get to moles, we have to divide by the molar mass of that particular substance. So hydrogen has a molar mass of 2.02. Now we know how many moles of hydrogen we have. Now we need to go to moles of ammonia. So now we multiply by the mole ratio. There's 2 moles of ammonia for every 3 moles of hydrogen. Now the units moles of hydrogen cancel out. Now we know moles of hydrogen. Now we need to get to grams of hydrogen. To get from moles to grams, you multiply by the molar mass of that particular substance. So ammonia has a molar mass of 17.04. Now the units moles of ammonia cancel out, and now we know the mass that can be produced from that. So again, this is a grams to moles to moles to grams problem. And on the mole map, again, we're going straight across this axis here on the mole map. Everything else is a variation of that same theme. For example, this one asks how many molecules of oxygen will be produced by the decomposition of 22 grams of hydrogen peroxide. So again, we need to write the balanced chemical reaction. I'd encourage you, write down what you're given. We have 22.00 grams of hydrogen peroxide, and we want to find out how many molecules of oxygen. So we have to go from grams of hydrogen peroxide to moles of hydrogen peroxide to moles of oxygen to molecules of oxygen. Or if you prefer the mole map, we are given grams of hydrogen peroxide. So we have to go to moles of hydrogen peroxide to moles of oxygen and then to particles of oxygen. So we will divide by the molar mass to get moles of hydrogen peroxide, multiply by the molar ratio to get moles of oxygen, and then multiply by Avogadro's number to get particles. So again, write down your given. We've got 22 grams of hydrogen peroxide. To get from grams to moles, you divide by the molar mass of that particular substance. Hydrogen peroxide is 34.02 grams. Now I have to get from moles of hydrogen peroxide to moles of oxygen. It's going to be a 1 to 2 ratio. There's 1 mole of oxygen for every 2 moles of hydrogen peroxide. That way moles of hydrogen peroxide cancel out, and then we have to get from moles of oxygen to molecules of oxygen. For every 1 mole of oxygen, there's going to be Avogadro's number of molecules, and so it calculates out to 1.95 times 10 to 23rd molecules. But basically we're going grams of known to moles of known to moles of unknown to molecules of unknown. One more sample problem. Ammonia reacts with oxygen to form nitrogen monoxide and water. What volume of nitrogen monoxide at STP can be produced from 1.2 kilograms of ammonia? So again, we have to write the balanced chemical reaction, and we are given 1.2 grams of ammonia, and we're asked what volume of nitrogen monoxide can be produced. So we're given kilograms, and so we're going to have to first convert to grams, because grams are what you find on the periodic table. So we're going to go kilograms to grams to moles to moles to liters. So again, if you want to look at the mole map, we're going to take our number of kilograms, convert to grams, then we go to moles, then to moles, then to liters. And the way that problem is going to look like this: to go from kilograms to grams, there's 1,000 grams for every 1 kilogram. And then to get from grams to moles, we're going to divide by the molar mass of ammonia. Then we're going to multiply by the mole ratio. There's going to be 4 moles of nitrogen monoxide for every 4 moles of ammonia. So again, always the one you're converting to on top. So 4 moles of nitrogen monoxide on top, 4 moles of ammonia on bottom. At this point, grams units have canceled, moles of ammonia have canceled. Now we know how many moles of ammonia, and if we want to find it at STP, then there's going to be 22.4 liters for every 1 mole. Moles of nitrogen monoxide cancel out, and we've got 1.6 times 10 to the third liters. So again, everything is just going to be variations of the same thing. We can go grams to moles to grams. We go grams to moles to particles. We go grams to moles to liters. We go particles to moles to particles. You get the idea. The only new step in stoichiometry is using the balanced chemical reaction to convert moles in one substance to moles of another substance in that same balanced chemical reaction.